Okay, hello everyone, and welcome to the first homework review of the semester, going over Chapter 1, Homework 1. So the way that these videos are going to work is that every Monday morning I'll go through quickly the homework results in Blackboard. I can see all the problems that you guys attempted and which ones you had the most difficulty with. So I'll choose a selection of those to go over in this video to try to help clear up some common misconceptions or other things that may have led to people not doing as well on those particular problems. This one will be a little bit short because on the first homework assignment there aren't too many problems that you guys had difficulty with, but as we go through the semester we'll have probably more and more things to cover in each of these, and you can expect them to be anywhere from 20 minutes to maybe 40-45 minutes at the most. So I encourage you to take a look at this to clear up any mistakes you might have made on the homework, and anytime you want me to go over a specific problem in this review video, you're welcome to contact me beforehand, as long as it's before Monday morning, and I'll be able to cover that one. So I do take requests on these as well. Alright, so getting into this, overall the performance on this first assignment was very good. The average for this one, if you guys are curious, was about 10.6 out of 12. Now keep in mind that's the, as far as I know, that's the average score, the average highest score. So remember that each person who attempts it more than once, we only count their highest score. So the score that went in the grade book was on average close to 11 out of 12 for everybody. So that's a pretty high average. We'll see that they'll trickle down as the semester goes on and the material gets more difficult. But like I said, we did pretty well on this one. There's just a few questions that I want to go over. The first one deals with the Rutherford gold foil experiment. And so most of the questions on this homework assignment were conceptual, and some of the multiple choice ones are a little bit tricky because you have to sort through all the choices, and there's 5, sometimes more than 5 choices. You have to figure out which one is the best answer choice to pick. So what we had was Rutherford bombarded gold foil with alpha particles. Alpha looks more like that. And found that a small percentage of the particles were deflected. So that is the Rutherford gold foil experiment as I explained it in class. Which of the following was not accounted for the model he proposed for the structure of atoms? So remember, using the scientific method, we have experiments that give us a series of observations, and we use those observations to propose a model or theory that explains those experiments. And so the result of the Rutherford gold foil experiment, the model that came out of it, was that you have a very dense nucleus. So this is what we call the Rutherford, or sometimes the planetary model of the atom. Well, we'll get into that later. Anyway, this is the Rutherford model of the atom, and this is what came out of his experiment with gold foil. You have a very dense nucleus, so very small compared to the size of the atom, and then you have your electrons are sort of in a diffuse cloud around the nucleus. So his experiment didn't really say anything directly about the location of electrons, but what it did say is that the nucleus, which is where, again, this is where all the positive charges are, the nucleus is very tiny and very dense, and then the electrons occupy a very large area around that nucleus, and overall there's a lot of empty space in an atom. So looking at this model, if you look at the answer choices, which of the following was not accounted for by the model? So the small size of the nucleus is accounted for by the model, so we're not going to choose that as our answer choice. The charge on the nucleus, so this is a part that Rutherford wasn't directly addressing, but his model does suggest that the positive charges are in the center, and the reason for that is that alpha particles are positively charged. And so whatever they're colliding with, whatever they're deflecting off of, must have the same charge. Remember, we're talking about charge-charge interactions. It was known that the electrons already existed, and his experiment directly probed what was the positively charged species in the atom. And so in order for the alpha particles to be deflected like this, they would collide with something that has the opposite charge, and so that means whatever this dense nucleus is must have a positive charge, and so that his model also accounted for that. Choice C is the total mass of the atom, and so this is the one that the Rutherford gold experiment doesn't really address. It tells us that most of the mass, or almost all of the mass of the atom is in the nucleus, but it doesn't tell us exactly what that is. And this was something that was addressed later on. And so that's going to be our answer choice. The one that is not accounted for by the Rutherford model is the total mass. Let's look at the other ones. D, the existence of protons. As we just said, the Rutherford model tells us that there's positive charges in the nucleus. We call those things protons. So the existence of protons must be accounted for by his model. And then finally, E, the presence of electrons outside the nucleus. Rutherford did not discover this. He was not, the electrons were found by J.J. Thomson earlier, and we had the oil drop experiment later on that kind of confirmed that. So he didn't discover the electrons, but his model includes the electrons still. He didn't do anything to disprove that. And so electrons are still an important part of the Rutherford model. And so really the only answer choice that makes sense is C. Rutherford's experiment and his model that he proposed did not say anything about the total mass. It just said about the location of the subatomic particles in the atom. Alright, so that's what we have for the first one. The next one here is about the Millikan Oil Drop experiment. So if we remember sort of the results of that experiment, before we get into the details of this question, the Millikan Oil Drop experiment said that, it gave us the charge and mass of an electron. And it sort of confirmed that the negative charges are contained in discrete particles, which we call electrons. So you can't just have, it's not so discrete, is it? In discrete particles. Or in other words, that the negative charge in an atom is quantized in some sense, that you can't have just any old value of the negative charge. And so what this question is asking us is, in a Millikan oil drop experiment, the charges on several different oil drops were as follows: minus 5.92, minus 4.44, minus 2.96, minus 8.88. The units are arbitrary. What is the likely value of the electronic charge in these arbitrary units? So what this question is asking us is, if we measure charge of electrons, and this is what, charge of oil drops, and this is what we get, what is the charge of a single electron? So that the electronic charge being the charge of a single electron. And so the concept that this is testing here is the idea that when you have charged oil drops that have negative charges, they don't all necessarily have the same charge, but they're all going to be some whole number multiple of a single electron. You can't have less than one electron in an oil drop to give it its negative charge. You can't have a fraction of an electron. So all of the charges that you measure have to be whole number multiples of each other, which means these numbers here, minus 5.92, minus 4.44, minus 2.96, minus 8.88, what we need to find is what is a common factor of all of those numbers, if you want to think about this mathematically. So the way we can go about this is we can write out all of our charges: minus 5.92, minus 4.44, minus 2.96, minus 8.88. We divide these by all of the elementary charges that are proposed as answer choices. So A is minus 1.11, B is minus 1.48, C minus 2.22, D minus 2.96, and E is minus 5.55. And when we divide the charge of an oil drop, this row here, by the charge of an individual electron, we should always get whole numbers. So an oil drop can have the charge of 1 electron, it can have the charge of 2 electrons, it can have a charge of 3 electrons, 4 electrons, so on. It cannot have a charge of 1.73 electrons or 2.85 electrons. It has to be the charge of a whole number multiple of whatever the charge on the electron is. So if we look at choice A, if the charge of an electron was minus 1.11, minus 5.92 would correspond to how many electrons? So we divide the larger number by this elementary charge here, and what we get here is whoops, didn't mean to zoom in there, sorry. If we divide these two, we get 5.33. Now we could check all the rest of these, but the point of the fact of the matter is, for this first choice here, we've gotten not a whole number of electrons. We've gotten some fractional number of electrons. So choice A, we don't even have to do the rest. We can rule that one out. Now choice B, if the charge is minus 1.48, if we divide minus 5.92 divided by minus 1.48, that would tell us that we have 4 electrons for this oil drop. This is oil drop 1, 2, 3, and 4. Let's number them. For oil drop 2, if we divide 4.44 by 1.48, that would be 3 electrons. 2.96 divided by 1.48 gives us 2 electrons, and 8.88 divided by 1.48 gives us 6 electrons. So this answer choice here looks like it makes sense. All of the oil drops have a charge that is a whole number multiple of minus 1.48, which would be the individual electron's charge. So choice B is the correct one. If we want to verify that the rest of them don't work, what we see for choice C is 5.92 divided by 2.22, again is a fraction 2.67, so that one doesn't work out. We don't even have to check the rest, although we could. If we have minus 2.96 is our electron charge, in this case the first oil drop would be a multiple of 2 of that, so that's okay. But if we divide 4.44 divided by 2.96, that would require us to have 1.5 electrons, which is not going to work. This would be 1 electron, this would be 3. So in order for this to work, all of these have to be whole numbers, so this one's not, so we can get rid of choice D. And then finally the last one, this would be divided by, so remember we're dividing minus 5.92 divided by minus 5.55 is 1.07, so that doesn't work either. So the point being that whatever the charge on the oil drop is, these numbers up here have to be whole number multiples of whatever the charge on the electron is. So the only one that works to give all 4 whole number multiples is choice B. So that's kind of more of a conceptual question. It required a little bit of math to sort through it, but the idea being that whatever the charge is on the electron in whatever units you're measuring it in this case arbitrary units as we're saying, the charge on an oil drop has to be a whole number multiple of that, because you can't have fractional electrons that would give you a partial negative charge. Alright, the next question deals with mass laws, and it's which of the laws are illustrated by the figure below. Alright, so if we look at the answer choices, we have all 3 individual mass laws, and then we have different combinations of them for choices D, E, and F. So we have to see which one of these are illustrated by this figure. So if we look at what we have here, we have a bunch of atoms on the left. We have 1, 2, 3, 4, 5, 6, 7 purple. And then for the green, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 green. And those are recombining in some ways to make this new picture over here where we have some molecules, we have some individual atoms left. And if we count up the total number of atoms, we still have 1, 2, 3, 4, 5, 6, 7 purple. And for green, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 green. Alright, so the number of atoms that we started with, 7 purple and 9 green, is the same as the number of atoms we ended up with after the chemical reaction. And so this would demonstrate the law of conservation of mass. Okay, because the number of atoms were not created or destroyed, matter was not created or destroyed, however you want to think about that, and the total number of atoms we had at the beginning is the same as the total number that we had at the end, and none of them changed into anything else. There was no change in identity either. Now in terms of law of definite composition, remember that law of definite composition tells us that a given chemical compound will have a certain mass ratio of the elements. And so if we look over here at the product side, we have the only compound that we have is going to be 1 purple and 2 green. So it's going to have a 1:2 ratio of purple to green. And so all of the compounds that we form, all the molecules that we form over here on the right side, have a definite composition, 1 purple and 2 green. So the law of definite composition tells us that a chemical compound has a fixed ratio of elements in it, and so that one's also demonstrated by this. Now, law of multiple proportions, if you want to think about whether this one is demonstrated, remember that for the law of multiple proportions we need 2 elements, but these 2 elements have to form 2 or more different compounds. And if they do that, those compounds will have different mass ratios. But in order for this law to even be demonstrated, we need to have 2 or more different compounds being formed. And if we look at the right side, all of the compounds, all of the molecules that form, again, have this same ratio, 1:2. So this picture does not show us two different compounds made out of these atoms, or two or more different compounds, so the law of multiple proportions is not demonstrated at all. So the first two mass laws are in fact demonstrated, but the law of multiple proportions is not included in this picture, and so the correct answer would be choice D, law of conservation of mass and law of definite composition. But in order to demonstrate the law of multiple proportions, you need to have two different compounds. In this picture we only have one, so it doesn't directly demonstrate that mass law. Alright, and then a couple other ones that we're going to go over. This was a free response question, and there was a variable input, so the question you may have had might not have the exact same numbers in it, but it was really the same format. We want to know what is the sum of the number of neutrons and electrons in the ion 73As3-. Okay, so our atomic symbol is 73As3-, and as we went over a few times in class, we have to just go through the different subatomic particles and find the number of protons, neutrons, and electrons using the different parts of this atomic symbol. So the first thing we need is the number of protons, which we abbreviate as the atomic number Z, and this one's not directly given to us when we write the symbol like this. So remember, as I said in class, very often in atomic symbols we don't put Z down here. So Z would go in this part of the symbol if it was there. It's not directly given to us, but for that we have to use the periodic table to find what Z is, the number of protons, or alternatively called the atomic number. So if we go to our periodic table and we find arsenic As is over here. It's atomic number 33. There's that 33 right above the symbol. So that tells us that every atom of arsenic, regardless of what isotope it is, regardless of what charge it has, every arsenic atom or ion will have 33 protons. That's what that number 33 means. So the number of protons is 33. Now we don't actually need that number to answer this question, but we need that number to find the number of neutrons and the number of electrons. We need it for both of the parts of the answer that we're looking for. So for the number of neutrons, remember that the mass number, which is A, is equal to Z plus the number of neutrons, or in other words, it's equal to the number of protons plus the number of neutrons. So our mass number for 73 arsenic is 73. That's going to equal the number of protons plus the number of neutrons, and that means we have to have 40 neutrons in this ion. Alright, because the sum of these two, 33 and 40, has to equal the mass number, which is 73. So we have the number of neutrons, but we also need the number of electrons to answer this question. And remember, for the number of electrons, a neutral atom will have the same number of protons and electrons, so our number of protons is 33. This has a 3- charge, so for each additional electron we have to add, for each additional charge we have to add one additional electron, so that means we're going to have 3 additional electrons, or 36 total. So to give us a 3- charge, we have 3 more electrons than protons, which is going to be 36, and so finally the number of neutrons plus the number of electrons is, let's do that in the right order, 40 plus 36, hang on, 40 plus 36, which would be 76, and that would be the number that you would type into Blackboard for this question. Okay? So it requires us to really be able to do all three, because we can't find the number of neutrons and the number of electrons without first knowing the number of protons. You have to go through the whole thing, but we know from the atomic symbol how to find the number of protons and using the periodic table to help us, and then from there we can get neutrons and electrons. Alright, the last one is the law of multiple proportions. We talked about this one a little bit in the context of a previous question, and this is the one that I said in class that I warned you would be the most conceptually difficult. So law of multiple proportions, we give 4 answer choices as well as none of these, and so let's see. If the same two elements form two different compounds, they do so in the same ratio. So this is almost right, and this is what a lot of you picked, but remember that multiple proportions says if we have two elements that form two compounds, or more, let's say two compounds, they can be more than two compounds in many cases, but if two elements form two compounds, they must have different mass ratios. That's what distinguishes the two compounds from each other. So the classic example of this that we gave in class is carbon and oxygen form two compounds. They're two very common ones that we know of: carbon monoxide and carbon dioxide. Carbon monoxide has one carbon, one oxygen, and the mass ratio would be about, would be about 43% carbon by mass. Carbon dioxide is one carbon to two oxygens, and the mass ratio would be about 27% by mass. And so when two elements react to form two different compounds, they will always have different ratios. And so this one is false because that word should be different. And so that's not going to be our correct answer. That's the one that most of you picked, I believe. If we look at the other answer choices, B, it is not possible for two elements to form more than one compound. Well, that's exactly what the law of multiple proportions doesn't say. That's the opposite of what it says. And as I just finished telling you, it's very common for two elements to combine in two different ratios to form two different compounds. Carbon monoxide, carbon dioxide being an easy example. There's some less common ones like water is H2O, and then you have hydrogen peroxide, which is H2O2. So again, the same two elements forming two different compounds with different ratios. So that's not going to be correct for the law of multiple proportions, because it is certainly possible to do that. C, the ratio of the masses of the elements in a compound is always the same. This one here is true, but this is a statement of the law of definite composition. Now, the law of definite composition tells us about the mass ratios or the mass composition of a single compound. And so this statement here is really just one way of saying the law of definite composition of compound. Because I can't write and talk at the same time. So choice C is the law of definite composition. That's exactly what that's telling us. So it's a different mass law. Here we're looking for multiple proportions. And then finally choice D, the total mass after a chemical change is the same as before. This one is the law of conservation of mass. So choice C and choice D are both true statements, but they apply to different mass laws than what we're looking for. And so, as it turns out, actually X that one out too, that's not the right answer. It's true, but it's not the right answer. Same with this one. And then, so the only one that works is E, none of these. And I know it's a little bit, psychologically challenging to pick none of the above as the answer. You always want to assume that one of the correct answers is there, but once in a while we will give you a question that has none of the above is the correct answer, and this is one of those. So the first two statements are not really true. They're related to the law of multiple proportions, but they don't actually say what it's supposed to say. And then choices C and D are true statements, but they apply to different mass laws. Alright, that takes me to the end of what I wanted to talk about today. Any additional questions on the homework, feel free to come see me during office hours or email me if that's more convenient. I can help you with those. And I'll be back next Monday with the second homework assignment, doing a review for that.